So the last segment that I would like to deliver is the magnetic field. We have been talking about gravity field. Now it's the magnetic field. So magnetic field. Now, we will be talking about magnetic characteristic of ferrous body first, because I think it's the most familiar thing for us. We know that that positive and positive, they do not like each other. Basically, they will never like match. But if it's like positive and negative, opposite poles, they will attract each other. And that's basically the characteristic of a ferrous body. A ferrous body itself is basically some elements in the table, like iron or Fe, that's ferro, and then cobalt and nickel, they are classified as ferromagnetic elements at and above room temperature, which means that they have high susceptibility to magnetization. I think I don't have to explain what magnetization is again. And then the field strength, the magnetization strength, depends on the applied magnetizing field. And even if the magnetization field is removed, the field might persist in that ferrous body. So we can say that materials that consist of these elements, they are defined as ferrous bodies. So this is basically the very basic equation. It looks very similar to gravity. So you've got the R in here, and then you've got the magnetic field that you want to calculate. Normally it's in nanotesla or NC. You've got the magnetic constant, depending on what material you're working in, and the point magnetic poles of strength. So where you are at your measurement area. We will talk about this later. So for example, before a magnetic field of B applied to a ferrous body, the ferrous body normally already have a magnetization, but it's very small, it's very scattered. It's like you've got a lot of needles inside of that. But when you apply a magnetic field of B, all the magnetic field inside the ferrous body will have the same direction as that magnet as that magnetizing field, just like in here. And when the B is removed, the magnetization is still, it persists at the ferrous body, but the strength might not be as strong as when it was applied, but it still remained. So magnetic field direction is a bit more complex compared to gravity directions, because gravity directions, it's always down, because everything, every single body on this earth will be falling down if we just make it in free fall. But magnetic field, it's a bit more complicated. So maybe we just illustrate it with a compass here. So you've got your north and east in here. So that's north and east. And we can imagine that if the needle at the compass is pointing somewhere, there's like a deviation to the north. So that's our horizontal magnetic field direction. We can compute the X and the Y, and the angle, the deviation between the north and the point, where the needle is pointing, is called the declination. So we can already know that maybe it's familiar to you that declination is basically the difference between the true north, or basically the geographic north, and the north that is pointed by the magnetic, which is the magnetic north. And then you've got also the vertical field. So the vertical field is, it's not only moving towards the horizontal one, but also vertically, just like this. So that's basically your Z, and the angle is called inclination. Again, declination is very important for navigation. Normally in any nautical chart, you've got the declination number. So basically the navigator knows, again, the difference between the geographic north and the north that is pointed by the magnet. And that's why normally we've got a declination map, and it is renewed by the IGRF every 5 years or so. What about the inclination now? That might be a question. So in inclination, it is very useful for signatures of ferrous body. For example, we've got a buried magnetic body. The ambient magnetic field is in inclination of like 60 degrees, which is in northern Mid-northern latitude, I will explain about the latitude later. So you've got the Earth, again, you've got the buried magnetic body, for example, a pipe, for example, and the distance is r, and this is basically the ambient magnetic field. That is this one, with an inclination of 60 degrees. So the magnetization in that body will follow the ambient magnetic field. And if you do a magnetic survey, it will look like this. That's your B. And you can see that the peak in here is not exactly on top of the body. That is because the position of the peak depends on our latitude. Because unlike declination that is just like all over the place, inclination actually has quite a good relationship between that number, the inclination number, with our latitude. So for example, near the equator, the inclination is almost zero, while on top of this, like near the North Pole, it's like 80 up to 90 degrees. So the signal of one body might be different if you are surveying, for example, in Indonesia. The magnetic signal might be different if you are surveying in, for example, at the North Pole or something like that. So that's basically what we are talking about now. The same magnetic body in 3 different locations has different magnetic anomaly signatures. That's our Earth. You've got a magnetic body in A, B, and C, exactly the same one, but it looks like this. So this is how it looks like at the North Pole, close to the pole. It will be situated almost on top of the body, and it's positive. While if it's in the equator, it will look like this. It's negative, but it's still on top of the body. But if you're in the middle, for example, at C, here, you will basically have something that looks like this. So you've got something that is positive, and then you've got a trough of negative value in here. Normally it's not as big as this magnitude, and then that's it. So that's very important if you're doing a survey with magnetic data. It's really important to consider where you are in this world, because it doesn't really behave the same way. That's it.